our critical values. Okay, so we have to find, you know, what we need to look for here. We have to find our critical value. Okay, the other side of this is the degrees of freedom for the numerator, right? And the numerator for us is degrees of freedom treat. Just as a reminder, that's k minus 1. How many groups we have? Minus 1. In this example, and you can look back, right? It's in our source table. Degrees of freedom treat is 2. We had 3 groups, minus 1. So our degrees of freedom for treat is 2. Okay. Here's a little hint for you guys. I mean, that's all it's really going to be, is right around this range. You're not going to have too many groups. We just wouldn't do that to you, right? So you're only going to have maybe 4 groups at the max. It's just not going to be like that. But if you had 5 groups, you know, you can figure this out. Okay, well, these are degrees of freedom, right? So you got to subtract 1. So we're not going to be looking at any numbers over here. That's meaning you have 11 groups, you have 12 groups, you have 13 groups. This is way too many, too big of a problem for us, okay? So we're working down here. So degrees of freedom 2. And then if we look over here on the side, it tells us degrees of freedom for the denominator, okay? And that is our degrees of freedom error. Look back at your table right here. Degrees of freedom error is 9. Okay, so 9, here's this one. Oops, that was off. All right, degrees of freedom 9, right? So we slide our fingers over and there are our critical values. The light face is the critical value at the 0.05, and the bold, the 8.02, is the light face for, or I'm sorry, is the critical value for the 0.01. Okay. So if we look back to this table that I've now scrabbled all over, he has it listed here that the F at a 0.01 level for a degrees of freedom of a 2 and 9 is equal to 8.02. That's what we found that right here, right? He could have listed the 4, the 0.05. He could have listed the critical value for 0.05. But like I was saying yesterday, that's great, right? 0.05 is great. That's significant for us. But if you have significance at the 0.01, you might as well report that, because that gives your results more power. There's more effect, if you want to think of it that way. Okay, so this is why they have that listed right here. And what he's telling you over here was that the P, the probability of finding an F of this magnitude, was less than a 0.01 chance, less than a 1% chance. Okay, so if we want to go back to some familiarity where we had our distribution, right? He has here the 0.02 at the, sorry, 8.02 at the 0.01 level, right? If we were comparing our F, our 11, I mean, it's out here, right? It would be way out there. So it is very within the rejection region. So in this example, we would reject the null hypothesis, okay? Oops, I don't know if I meant to do that. All right, I hope that makes sense a little bit with that table. So I'm going to move here now. This example is a little more complex. It's complex for a couple of reasons. We have now 4 groups, so our K is equal to 4, right? We have these schedules of reinforcement, okay? Here, we do see that they list the N for each group, okay? They still, for some reason, didn't put an in total, but you know, who am I, right? And I want to say we came up with 22 yesterday for our in total. And actually you can see it right here in that formula, right? In total, that formula right there. So that's correct, okay? You would just add up the ins, that's how you get that. They did list our means here, okay? I don't know, let's see, partial analysis of minutes to extinction. Okay, so how many minutes does it take till the animal no longer pairs that behavior, to see, you know, will they quit pushing the button to get the food, based on whichever schedule this is. Okay, I think I remember reading a little bit in the book that this is like a continuous. This is the animal gets rewarded after 2 presses of the bar. This animal gets, or these animals get rewarded after 4 presses of the bar, and these animals get rewarded after 8 presses of the bar. Okay, and we know if you're constantly reinforcing something, and then for some reason, if you stop doing it, those animals are gonna they're going to learn real quickly. They're like, I'm not going to do that behavior anymore because I'm not getting rewarded. Once you start kind of adding in where you don't get rewarded every time, you get rewarded a little bit later, then obviously it gets harder and harder to extinguish that behavior. And that's what this is showing here. Okay, so the means are you can see that they're clearly different, right? How many times or how many minutes does it take before that animal stops that behavior? Okay. So some of these values, you don't need to know this because I'm not going to have you calculate these, but just to look over the formulas, okay? SS total, like I had said before, it's a little bit of a pointless number. It's down here, and I say that it's pointless because you do not use it to calculate anything. Only these numbers up here go into calculating F. These are just kind of sidebar numbers that don't really do anything. Okay, now they serve as a way for us to check ourselves, right? We can make sure we're calculating our numbers correctly, but they're not really necessary. So that's SS total, okay? And you take the sum of all the x's squared, okay? So you would add up all these squares, the bigger numbers. Oh, they don't have it listed there, right? But you would take this number and this number and this number and this number, and you'd add them up, okay? And then you take the sum of x, which is just the sum of x here, total, so you'd add all those up, and you square it and then divide by the in total. Okay, so that's what's happening right here, and this is how they get that 273.273. Okay, here is our SS treatment, right? But they say schedules because it's our groups and we're looking at the different schedules of reinforcement, okay? And this formula looks a little complex. He's a big sum, right? So he's saying add up what all is inside of here, okay? And when we see these little t's, this is telling us like for every group. So, or do this for each group, okay? So the sum of x for group A squared divided by n for group A, and then you're going to add it and do it for group B, and you're going to do it for group C, and you're going to do it for group D. Okay, so they took the sum of x, this 21 for this first group, and they squared it, and they divide by how many people were in, or rats or whatever were in this group. Then they did it for the second group right here. You can see they took the sum of x, 56, they squared it, and they divided by how many people were in that group, which was 7. Okay, then they did it for the next group, 54 squared right here, divided by 5. Okay, and then for the last one. So this is how you calculate those. You do have to subtract off the total, and so that's just kind of this little side part that you do to that, and it's right here. Okay, and then SS error is very similar to what we were doing all along, and if you look at it, it looks like our standard deviation, the top part of our formula that we've been very used to doing, right? We take the sum of x squares, right? Or the sum of the x's squared for each group, and minus it by the sum of x that we're going to square, and then divide by the n for each group. And so here's where we have that, right? You have the 99, the 21 squared, and divided by the 5, right? And then you do it for the next group, the 476 minus the 56 squared, divided by the 7. And you just repeat it over and over and over again, right, for each group. And that's how you calculate our SS error, okay? And again, I'm not going to have you do this, but this is just, that's where those numbers are coming from. Okay. So again, it's, and the nice thing, guys, really, is moving forward, I mean, you really don't have anybody that calculates ANOVA by hand. Okay. Why? And in fact, in statistics, in like the academia world, where you have statisticians kind of like fighting each other on what's the best statistics to do, they are now kind of fighting with each other about, do we need to waste people's time teaching them how to do it by hand when we all know darn well nobody does it by hand? Let's just teach them how to do it on the computer. And then you have people that are like, no, if you just teach them how to do it on the computer, they don't really understand where the numbers come from, and they don't really understand what they're finding and what they're calculating. I stand in between the two, right? I fully believe that if you calculate it just like with that, where we were subtracting off the mean from each group, you start to understand a little bit of where those numbers are coming from. But I also realize that a little bit of this is just, okay, it's just a little bit too much, right? And if we can plug it into the computer and we can get a printout where we see these things, then we can say, okay, let's just teach them now, what they're looking at, right? So they got their SS's, okay, degrees of freedom, right? They had 4 groups, so we had 3. Is our degrees of freedom treat. Degrees of freedom error is in total minus K. So it was 22 minus 4, which gave us that 18. And then just a little check, the in total, or the degrees of freedom total is in total minus 1. So 22 minus 1 gave us 21. Divide these across. These are going to be your MS's, right? And then to calculate our F, ultimately, divide this number, and then you get your F, right, of 17.16. 17.16, I think we've kind of learned by now, is a really big obtained value, right? And so we're fairly confident no matter what that that's going to be significant, but let's see at what level is it significant. So I like this table because he lists both of our critical values at the 0.05 and the critical value for the 0.01. But let's go back and check, right? So he's mentioning here we're using degrees of freedom of 3 and 18, 3 and 18, okay? So let's look at this one. Is 18 on there? No, it's not. This one stops at 13, so we need to use this table. Okay, here's 18. Oops, I didn't mean to do that. So here's 18, okay? And 3. Sorry, I scrabbled over them. And here is that intersection. And so we have 3.16 for the 0.05 and 5.09 for the 0.01, which is exactly what he listed, right? Did I say that right? 3.16, yeah. And then the 509, okay? So 17.16 by far exceeds those critical values, okay? So if we want to do, we would say the 5% or the 0.05 would be right there, and then the 509 would be right there. Well, 17 is like off the computer. It's off the screen, right? It is by far way out there, okay? And so this is why they have P listed as the probability of finding 17.16, which would be way out here. The probability of getting that result is less than a 1% chance. Okay, or the P is less than 0.01. So in this example, right, for sure, they're going to reject the null hypothesis or reject the HO, right? And so now we sit here and we say, well, what does that mean, right? What does that mean? What did we find? We're like, who knows, right? What we found is that the minutes to extinction based on the schedule reinforcement is significantly different. The minutes that an animal will stop doing a behavior is contingent on what schedule of reinforcement it had. So ANOVA tells us, okay, cool, you got a difference, right? You have a significant difference in the means, but it doesn't tell us where. It doesn't tell us which means are different. We know we got a significant difference, but we don't know which ones. Obviously, logically, we could say, well, at least the lowest and the highest are different because we got a significant difference. So at least we could assume, right, the highest and the lowest are different. But we don't know, is there a difference between 10.8 and 12.6? I don't know. Is there a difference between 8 and 10.8? Is there a difference between the 8 and the 12? Is there a difference between the 4 and the 8? We don't know, right? So the more groups you have, I guess the more confused you are, or the more, we don't know. We don't know where they are. We don't know which differences exist. But don't worry, somebody thought this out, all right? So when you get a null hypothesis, or when you, let me start over. When you get to reject the null hypothesis, you have to do a multiple comparisons test to determine which means are different from the others. Right? It tells you that there is a difference, but it doesn't tell you where the difference is. So you have to do a multiple comparisons test. And there are two types, a priori and post hoc. A priori sounds exactly like that word right there, prior. Prior. Beforehand. This is a test that is built into the data analysis so that once you run the data, it will tell you which ones are different. This may or may not be, I am sure it's in SPSS. I'm sure it's something that would just, the computer would just do it, okay? The most common multiple comparisons test that are done are post hoc, and the most popular of the post hoc is the Tukey test. Okay, the Tukey HSD. HSD stands for honestly significant difference. There is a significant difference between the means that you test. Okay, and that I went in yesterday and I went way over explaining that you do the means, you get you have to calculate standard error, you get a HSD, you get a value for that, and then you have to go to another table. It's the Tukey test table, and you have to look up another critical value. I'm not going to go into that today because it's not anything you're going to have to do. Okay, so right now I just want you to know why you would do a multiple comparisons test. What two types are they, or are there? And then a little bit like define a priori, define post hoc. Post hoc literally means, I don't think it's on there, I don't see it. It literally means after the fact. That's what post hoc stands for in Latin, I guess. After the fact. Okay, that's what post hoc, after the fact. So you do this after the data is already analyzed. And that's it. See, I get so much better the second time around talking compared to the first time. And so I apologize for that. So anybody, you know, now that it's the end of the semester, that probably doesn't help you out too much. Maybe don't waste your time on the first video and just watch the second video. It's much more concise, and I've learned from my errors from the day before. So that's all you need to know, which is a lot. I'm recognizing that. I'm not dismissing it. That is what you need to know from ANOVA and from chapter 11. Are there any questions? That's pretty cool.
And if you could stop giving me minor heart attacks, that would be great.
Deal, Cody. It's a deal.
Cool. Well, yeah. If you would, email me if I need to do anything else to change that.
No, you don't. You don't. I'm going to go do it right now. I promise you.
Cool. All right. Well, I was actually going to use this as a good excuse to not go to work today, but I guess I'm going to go to work. So.
Oh. Well, all right.
Yeah.
I mean, I hate to make you have to go to work. It's always nice to have a day off, but.
Yeah. I was going to use this as an excuse, but I don't think it's going to fly.
You don't think it'll fly? All right.
No, probably not. So.
Well,
I appreciate your time. I will
be
sure to study up on chapter 10 and 11 again in the book.
Okay. Okay. Have a great.
You said tomorrow you're going to do 4 o'clock?
Not tomorrow. Friday.
Or Friday, yeah.
Yeah, Friday at 4.
Okay. I'll try to make that one also. If not, you're going to upload it, right?
Yeah, I'm going to post the review and all that good stuff. Okay.
Cool. Okay. Thank you, Ms. Valles.
All right. Thank you, Cody. Have a great day.
You too. Bye-bye.
Okay. Bye-bye.
This today was actually a lot more simpler. I feel like it just either because you said most of it yesterday, but it just felt so much like it made, not that it made more sense. Maybe I just got it because I listened to it all day yesterday. And then it just was more like simplified.
Okay. Yeah. And yes, probably a combination of both, right? You sat through yesterday, and then hearing it for a second time, and definitely, you know, whatever I do it twice, I always find the errors in my ways. I mean, and that's just something, you know, even if like say face-to-face, if I have 2 intro classes, the very first intro class, is one way, and I can always tell my second one, it just goes so much different. It's just smoother. And it's just, you just kind of, it's a little practice run, right? So hopefully, yeah, this makes a little bit more sense today.
Yes, it did.
Okay.
It was a lot easier, or a lot smoother.
Smoother, yeah. And you could say easier. That's fine. That's good. I'm glad you're using that word. Yeah.
Yesterday I just felt like at the beginning I felt like you were speaking French or German, or like.
Yeah. Yeah. Okay. Well, that's good. That's good.
It made like, how you have said from the beginning, some people just like the math part, and some people just like the
words.
Yeah, the words,
Yeah.
right?
Yeah.
I seem to do a lot better with the numbers.
Okay.
Than with the
why and
the why and
yeah.
Explanation, right? And I think it's because of that contemporary math class that I took.
Yeah.
Because it was not so much about the words, right? It just was the formulas. They gave you the formulas, they gave you the numbers, and all I had to do was work it out.
Right.
Same here, right? So when I'm like hearing everything else, it's just like, it's too much information and I don't know what to do with it.
Yeah. Yeah. No, I get you. And yeah, but sometimes, yeah, it's just different.
That class, it was at the beginning of the pandemic. So I went to class at the beginning, and then that's when the pandemic hit. So it was like, like I did panic in that class when we were no longer going up, like after spring break. I was
right.
like, oh God, how am I going to do this class? Like I am the type of student, as you've seen, I will either go to your office in between at some point throughout the year because of something, like I always feel like I need more, like reassurance. That's my issue. I always need reassurance. So with this class, when we started seeing formulas, I was like, oh my God, I'm gonna panic. Like I did panic. I do panic. But then once I get going and I just see numbers and I don't look at the words, then I do better.
Right. Yeah. No, I get you. And you're not alone at all, right? There's a lot of people. And then there's plenty of people that are like, I like the words, I hate the math. So, but I'm glad. I hope this makes a little bit more sense.
Yes. I mean, I got it. Like I said, me listening to it yesterday and me coming again today just made it more